Hello, everyone. We'd like to introduce our CVPR paper, named Clipping, Distilling Clip-Based Models with a Student Base for Video Language Retrieval. Pre-training a vision language model, and then fine-tuning it on downstream tasks, have become a popular paradigm. However, pre-trained vision language models with the transformer architecture usually take long inference time. Knowledge distillation has been an efficient technique to transfer the capability of a large model to a small one while maintaining the accuracy. However, it faces many problems when applying KD to the multimodality applications. In this paper, we propose a novel knowledge distillation method, named clipping, where the plentiful knowledge of a large teacher model that has been fine-tuned for video language tasks with the powerful pre-trained clip can be effectively transferred to a small student only at the fine-tuning stage. Knowledge distillation is a simple yet effective technique to improve the performance of a learning model. Earlier works transfer knowledge embedded in the logits learned in a large teacher model to a small student model without sacrificing much performance. Recent works use intermediate layers of the teacher to supervise student, for example the tab KD in Figure 1b, where each layer of the student learns the knowledge from multiple layers of the teacher. For multimodality KD, CMAD designs a fusion encoder model as the teacher and introduces cross-modal attention knowledge to train the dual encoder student model. The contributions of our clipping are summarized below. First, we introduce an efficient approach to distill both the vision knowledge and the cross-modality knowledge from teacher to a small model at the fine-tuning stage. Second, we propose a new layer-wise alignment scheme, called Student as Base, where the student's layers can be regarded as the bases of the teacher's feature space, forcing the student model to full absorb the knowledge of the teacher. Third, we present an effective cross-modal knowledge distillation, which includes knowledge from both the global and local video caption distributions. Last, clipping achieves 91.5% to 95.3% of the performance of its teacher, with its vision encoder being 19.5x smaller. Clipping also significantly outperforms a state-of-the-art small baseline. Clipping is comparable, or even superior, to many large pre-training models. In Figure 3, we show the overview of clipping. There are mainly four knowledge distillation parts: temporal KD, spatial KD, SAB KD, and cross-modality KD. The clip's vision encoder is a transformer. Among them, our novelties and improvements mainly come from SAB KD and cross-modal KD. First, we introduce the SAB KD. We first show the advantage of our SAB KD over traditional TAB KD. Obviously, as shown in the equation 1, the knowledge of the teacher LT1 or LT2 is the linear combination of LS1 and LS2. In other words, LS1 and LS2 are the bases of LT1 and LT2 of the teacher. In the equation 2, it can be seen that the teachers LT1 and LT2 are as the bases for LS1 and LS2. The equation 2 can be converted to equation 3. Although it seems that SAB and TAB have the same matrix representation, TAB is unable to get a similar result as SAB, because the coefficients are easily arbitrarily large during optimization if it is converted to SAB's form. For this reason, TAB KD is more likely to get to a local minimum during training. As for the cross-modality KD, we characterize the cross-modal distributions from two perspectives: global video caption distributions of the teacher and local video caption distributions of clip. For our cross-modal KD, it not only forces the student to learn the video caption distributions from the teacher, but also obtains the local frameword knowledge from the powerful pre-trained clip. Therefore, the teacher's knowledge can be effectively transferred to the small student only at the fine-tuning stage. Our experiment shows that only when joint trained with SAB, our local video caption distribution alignment shows its advantage, which also verifies the effectiveness of SAB. In Figure 7, we visualize the frameword alignments with and without SAB KD. Figure 7a is the result of the clip in Clip 4 clip. Figure 7b is the result of our model without SAB KD, but with the previous TAB KD. It can be seen that the frame word alignment with cdddd shows clear and correct word level attentions like clip. But with cdddd, the most important words, example, naked, and child, cannot be noticed. Instead, some insignificant words are activated. In Table 1, we compare the proposed model clipping with 8 state-of-the-art methods on MSRVTT. In Figure 6, we show the performances and flops of these models. Among previous models, MDMMT has the best performance and ALL-in-1S is the fastest. Clipping not only obtains relative 4.6% performance gain over MDMMT, but also is faster than all-in-1S. Table 2 provides the details of flops and parameters for each module of our method. From Table 3, we can see that without any KD, it gets extreme low accuracies. When simply adding the temporal KD and spatial KD, rank 1 increase significantly. When we further add SAB KD, and then global and local cross-modality KD, clipping's performance rises gradually. This study shows that all these key components of clipping are effective. In Table 4, we compare the proposed SAB KD with the previous OL2 OL KD and TAB KD. The last 2 rows of Table 4 verify that the masking is beneficial. In Figure 7, we show the SAB property holds. In SAB KD, the student has 4 layers and the teacher has 12 layers. We randomly pick 3 image examples, and for each example, we select the features of 1 random token. After training, the linear combinations show feature patterns very similar to the teacher's features. This property verifies that the teacher's knowledge is fully absorbed by the student. To verify the advantage of our SAB KD, we show the linear combinations results of SAB KD and TAB KD in Figure 8. It can be seen that TAB KD is not equivalent to our SAB KD and does not have the property of the student as the base of the teacher. In this paper, we propose a novel and efficient knowledge distillation method that is specially designed for small vision language models. Clipping significantly outperforms the state-of-the-art and is comparable or even superior to many large pre-training models. In the future, we will apply clipping to other vision language models for compression. Thanks for your attention. If you have any question, please contact us.